Thank you for the introduction. Uh, Very good morning. So the topic of my presentation is airflow optimization for olfactory display using Inkjet devices. And I am Nilava Debabhuti. I'm associated with the Institute of Science Tokyo. So, so today I'm going to briefly discuss about the olfactory display, and here are my outlines. So I will go through some of the problem statements, my objective, system overview and the basic research, and concluding with the research and discussions. So as you can see that olfactory display is a device that is dedicated to scent reproduction, and it creates multisensory experiences. And recently there are a lot of researches going on, and the application is based on various domains including multimedia as well as VR, and it uh, the, the, the smell plays a very important role in evoking emotions in persons. And the olfactory displays become very essential where there is a requirement for spatiotemporal variations in the scent delivery. Now, coming to the problem statement, so generally the olfactory display operates by blending different kind of scents in a immersive sensory experiences. So uh, the main target is to recreate smells for different purposes. Now, initially the headspace system combined with solenoid valves were used, and there was many problems with accurately determining the blending ratios in the gas phases. And another problem was the narrow dynamic range, which hinders different kind of scent reproduction. So in the recent researches, so we are using the Inkjet devices, and it is capable of ejecting very tiny droplets in the range of picoliters. And in that case, it expands the dynamic blending ratios as well. And for this purpose, so we are using the electroosmotic pump, and which effectively controls the back pressure. So I will discuss the uh, arrangements in the next slides. And for this, so as we know that for the scent, the airflow is a very important parameter. So uh, the user experience the smell due to the airflow. So the main purpose was to accurately optimize the airflow for a stable scent presentation. So now coming to the system overview. So this is our system, and it consists of, as I mentioned earlier, a electroosmotic pump along with the inject device, and it is connected to a PC, and the main controlling unit is a FPGA unit, Altera Cyclone 5, and it's connected to a MATLAB interface, and this FPGA is connected to a DAC, analog devices, and it controls the uh, voltage of the electroosmotic pump as well as the frequency of the inject devices through the FPGA. And as you can see, the main concept is to accurately blend different type of order droplets, and it blends on a microceramic heater. So we used a microceramic heater here to effectively evaporate the uh, droplets, and it with the airflow channel, so we can easily send the mixed order to the user. And this is the software interface. So we developed a MATLAB GUI that can effectively control the inject frequency as well as the electro-osmotic pump voltage. And we can also set the droplet times or the olfactory display time. And in our case, we are using currently 4 channels. So this is the overall uh, software interface. Now coming to the olfactory display setup with as a microceramic heater and DC fan. So the main purpose of the microceramic heaters is to effectively uh, evaporate the droplets. So in this case, this is a EO pump with an inject device, and uh, for the microceramic heaters, so earlier we used to use SAW devices, But for the microceramic heater, we can achieve a very low power consumption with a simple driving circuit. And due to the plate-like structure, it aids in rapid vaporization of droplets, and it's connected to a regulated DC supply with a temperature monitored by a infrared thermometer. And for the airflow management, so we used a 12-volt DC fan and with a 3D printed holder, so that drives the airflow through a proper channel. And for the measurement and evaluation, we used a PID module, RA3000 plus, and the distance between the PID module and the point of dispersion was set to around 0.5 centimeter. So now coming to the temperature control. So we we analyzed the voltage with the microceramic heater, and we can see that the microceramic heater in this case was tested for 0 to 20 volt, and you can see that it can achieve around 326.5 degrees Celsius at 20 volt. And right now, for our experiments, we are using ethanol, and we can easily get a sufficient boiling voltage, or sorry, sufficient boiling point for ethanol at around 5 to 10 volt. So in this case, for measuring the temperature, so we use the infrared thermometer. Now for the analysis of the airflow, so there are two types of positions were considered in this case. So in the first position, so front and back. So first the DC fan was set in front, and in the second case, the DC fan was set in the back to properly optimize the airflow for getting a optimized result. So when the DC fan was set in the front, so as you can see that, so this is the block diagram, and as you can see that the point of PID module and the DC fan was set to 0.5 centimeter, and you can see that. So, and for this experiment, so we used 5 different frequency of inject devices. So starting from 100, 300, 500, 900, and 1000, and the operation duration was set to 30 seconds. So this is the result, and you can see a linear decrease in the PID responses with the decrease in the inject frequency. Whereas when the DC fan was placed at the back, so a higher frequency was observed, but in this case you can see there was a nonlinear trend in the PID output module, and the reason I will be discussing shortly. So in the previous case, so as you can see that the evaporation of the order molecules is directly sucked into the DC fan, which gives a proper estimation of the PID responses. Whereas in case of the second experimental module, where the DC fan was placed at the back, so there was a chance of there was a chance of disproportionate airflow, and which results in inaccurate PID module sensing. And in case of the previous device, and in case of the previous device, you can see that there was a lower PID responses. So this may be due to the absorption of the 3D printed module of the DC fan, which was not seen in the next case. So these are the probable reasons. And for the repeatability, so we checked the PID responses of 1000 Hertz for 30 seconds, and these are the responses. In this case, there are two kinds of results we can achieve. So for the front placement, we can see a consistent repeatable output with a maximum concentration around 400 ppm, and some order molecule loss due to the absorption, but the responses remained stable. and the post-dispersion noise due to the ethanol evaporation absorption by the DC fan leading to odor retention and potential contamination. And for the back placement, we got a higher concentration as there were no uh, loss due to the absorption due to the 3D printed module, but the responses were not that repeatable and inconsistent. And however, we can also see that the PID responses get back to their zero state after the dispersion stops. So coming to the conclusion, so we uh, incorporated microceramic heater that achieves a rapid evaporation with a surface temperature up to 326.5 degrees Celsius at 20 volt. And this provides a viable alternative with low power consumption with a simple driving circuit for effective evaporation of aroma particles. And in this experiment, so we consider two positions for DC fan, front and back, and the front placement offered more stable and repeatable output. So that's all for my presentation. And for the challenges and future work, the front fan position showed some absorption issues due to reducing the PID responses over time. So for the future studies, for addressing this problem, so we are going to test with alternative materials, 3D printed materials like stainless steel for the fan adapter to enhance the repeatability and improve the long-term performance. So these are all the future works. So thank you. Thank you for your time.